Earth's origin. Learning objectives: explain the hypotheses that scientists have about early Earth, describe the theory of plate tectonics, list the processes that change rocks over time, explain how to date events in Earth's history, describe how the geological timescale was established and its major divisions. Earth's formation and structure. Earth and the rest of our solar system formed from the cloud of gases that were drawn together by gravity over time. The planet cooled and formed the layered structures seen to the right. For millions of years, Earth remained a mass of liquid rock, or magma. During that time, heavier elements such as iron and nickel sank towards the planet's center, and lighter elements cooled and collected near the surface. As Earth began to cool, three layers formed: the crust, the mantle, the core. The crust is Earth's thin, solid outer skin. The mantle, which makes up most of Earth's mass, is mostly solid shell that stretches from the crust to the depth of about 2,900 kilometers, about 1,800 miles. The crust and outermost part of the mantle together form the geological unit called the lithosphere, which means sphere of stone. Earth's metal core is incredibly hot. These three layers together form the geosphere. The Earth's surface cooled enough to allow solid rocks to form. Its lightest components escaped to form a primitive atmosphere. Earth's early atmosphere contained little to no oxygen. It was mainly composed of carbon dioxide, water vapor, and nitrogen, with smaller amounts of carbon monoxide, hydrogen sulfide, and hydrogen cyanide. Because of these three gases, the sky was probably pinkish-orange. If you had been there, a deep breath would have killed you. As Earth continued to cool, water vapor condensed and fell as rain. Further cooling allowed the rain to remain in liquid form on Earth's surface. Before 4 billion years ago, water began collecting to form oceans. These early oceans, along with streams and collections of fresh water on land, formed the hydrosphere. During the 1950s and 1960s, Earth scientists placed together enough data to create and support the theory of plate tectonics. The theory of plate tectonics explains how and why Earth's lithospheric plates moved relative to each other as a result of convection currents in the Earth's mostly solid yet slowly flowing mantle. Plates are set in motion by convection currents in Earth's mantle. These currents rise and create new crust in some areas and fall in other places. Mid-ocean ridges are where plates move apart. Subduction zones are where plates collide. Volcanoes are known as hotspots, and where continents collide are where mountains are built. Weathering, erosion, and deposition. Many interactions between the geosphere, atmosphere, and hydrosphere break down and chemically change rocks at or near Earth's surface. This process is called weathering. Some different types of weathering are shown in these pictures below. If water enters cracks in rocks and then freezes, it expands. That expansion can break rock into smaller and smaller pieces. Other kinds of weathering involve chemical interactions that change the minerals that make up rocks, weakening them. Oxygen, for example, combines with iron-bearing minerals, changing their structure to form new oxide minerals similar to rust. After rocks have been broken down by weathering, smaller particles can be carried away by wind, water, or ice in the form of glaciers. In addition, some components formed or released by weathering can dissolve in water, be carried either into the ground or through rivers and streams to lakes and in the ocean. Over millions of years, rain flowing over land as dissolved, carried, or deposited salt minerals into the oceans form the salty seas as we know them today. When small particles of sand, silt, clay, or lime carried by streams or rivers reach a large body of water, they are often deposited on the bottom forming layers of sediment. Over long periods of time, as those layers build up, pressure and chemical processes can compress and transform these sediments into sedimentary rocks. Many sedimentary rocks also form from the chemical precipitation of dissolved sediments or form accumulations of wind-carried desert sand. Sedimentary rocks are particularly important in the studying of history of life, because if sediments build up quickly, they can bury dead organisms before their remains are eaten or scattered by scavengers. Once that happens, these buried remains can become fossils. The disciplines of earth science and paleontology try to describe and understand the history of our planet and the evolutionary history of life. Both these efforts require that we learn how to place dates on rocks, fossils, and important events in the history of Earth and life. As you have seen, sedimentary rocks are formed in layers. So unless some major geological phenomenon has twisted and distorted these layers, layers that formed first are found underneath layers that have formed later. By examining and comparing rock layers exposed at different places across the landscape, geologists can determine the order in which these rock layers have formed, and which layers are older than the others. This process, which geologists use to place rocks in chronological order, is called relative dating. Because sedimentary rock is formed as layers, lower layers of rock, and the fossils they contain are generally older than the upper layers. This process of relative dating is often extremely useful, but cannot determine the absolute ages of rocks in the order that they are placed. To help establish the relative age of rocks, layers, and their fossils, scientists use index fossils. Index fossils are distinctive fossils used to establish and compare the relative age of rock layers and the fossils they contain. The absolute age of rocks can be determined using radiometric dating. This technique relies on radioactive isotopes, which decay or break down into stable isotopes at a steady rate. A half-life is the time required for half of the radioactive atoms in a sample to decay. After one half-life, half of the original radioactive atoms have decayed, as shown in the graph. After another half-life, another half of the remaining radioactive atoms will have decayed. Radiometric dating uses the proportion of radioactive isotopes and stable isotopes to calculate the age of the sample. The most useful rocks for radiometric dating are the rocks formed directly from magma. Different radioactive isotopes decay at different rates. Elements with short half-lives are used to date recent rocks, and even more recent fossils. Elements with long half-lives are used to date older fossils. Consider how we time sporting events. For example, a 100-meter dash, a coach depends on fast-moving second hand of a stopwatch. To time a marathon, the slower-moving hour and the minute hands are useful for timing that race. Researchers use techniques to put fossils in order from oldest to youngest and to figure out how old the fossils are. Recent fossils can be dated directly by using an isotope known as carbon-14, which has a half-life of roughly 5,730 years. Carbon-14 is produced at a mostly steady rate in the upper atmosphere. Air contains a tiny amount of carbon-14 in addition to the amount of common, stable, non-radioactive form carbon-12. Plants take in carbon-14 when they absorb carbon dioxide during photosynthesis, and animals acquire it when they eat plants or other animals. Once an organism dies, it no longer takes in the isotope, so its age can be determined by the amount of carbon-14 remaining in its tissues, such as bone or wood. The relatively short half-life of carbon-14 limits its use to organisms that lived during the last 60,000 years. After 10 half-lives have passed, less than 1,000th of the original carbon-14 remains in the sample, which is usually too little to accurately measure. Older fossils can be directly dating using isotopes with longer half-lives to date the rock layers close to those in which fossils are found. Isotopes useful for dating older fossils include potassium-40, which half-life is 1.26 billion years, uranium-238, which half-life is 4.5 billion years, or rubidium-87, which half-life is 48.8 billion years. These studies provide direct physical evidence for the ages of index fossils that identify periods in Earth's history. These dates provide information using the document the rates at which groups appear, evolve, and become extinct. For the next 2 slides, make sure that you read the slide from the bottom to the top. The geological time scale. The geological time scale is based on both relative and absolute dating. The major divisions of the geological time scale are eons, eras, and periods. By studying rock layers, the index fossils, early paleontologists placed Earth rocks and fossils in order by relative age. As they worked, they noticed major changes in the fossil record at boundaries between certain rock layers. Geologists used rock layers boundaries to determine where one division of geological time ended and the next began. Because these divisions of geological time were described in the way, the lengths of ages are not consistent. For example, the Cambrian period began at 542 million years ago and continued until 488 million years ago, which makes it approximately 54 million years long. On the other hand, the Cretaceous period was 80 million years long. Long after the time scale was established, geologists used radiometric dating to assign specific ages to the various rock layers. Researchers are still testing, verifying, and adjusting this time scale. Geologists recognize 4 major divisions of geological time, which they call eons. During the first rocks formed in the oldest eon, spanning time from Earth's formation to about 4 billion years ago. The Archean era, or eon, during which life first appeared, was followed by the Hadean. Eons are further subdivided into eras. The Phanerozoic eon, for example, is divided into the Paleozoic, Mesozoic, and Cenozoic eras, which are then subdivided into periods, which range in length from nearly 100 million years to just under 2 million years. The Paleozoic era, for example, is divided into 6 periods, including the Permian period, for example. The divisions of the geological time scale were named in different ways. The Cambrian period was named after Cambria, an old name for Wales, which is named for the rocks at the time that were identified that were found in the area. The Carboniferous was named after carbon-bearing period, is named after large coal deposits that were formed during that time. Geologists started to name divisions of the geological time scale before any rocks older than the Cambrian period had been identified. For this reason, all the geological time before the Cambrian was simply called Precambrian time. Precambrian time covers about 90% of Earth's history. The amount of time covered by the geological timescale is so long that it's almost impossible for most of us to really understand how long ago events in Earth's history occurred. It is also difficult for us to realize what tiny portion of time humans have been around. On the geological timescale, even 1,000 years is like a passing moment. In this clock, notice the Precambrian time, when life was just beginning, covers the largest part of the clock face. In contrast, human history, or the modern human history, fits only about a minute.